Hello, everyone. I am Wang Yufei from Northwestern Polytechnical University. Our work have been accepted by ICCV 2023. As is well known, acquiring accurate and dense scene depth plays a fundamental role in various applications. However, existing depth sensors have inevitable limitations for both indoor and outdoor scenes. For example, the depth acquired by TOF camera and LiDAR is too sparse to be used directly. Thus, depth completion, namely estimating the dense depth maps from sparse distance measurements, has attracted widespread attention. Recently, deep learning-based methods have shown dominant performance for this task. These methods typically predict dense depth from sparse depth by massive stacked filters and layers. Since RGB images contain rich semantic cues, many RGB-guided methods are proposed. However, the direct regression method requires massive learnable parameters to learn robust features. They usually require heavy computing resources, which fail to be applied in the real world. In addition, some spatial propagation networks are proposed to refine the output of the direct regression methods by predicting pixel-wise kernels. Although existing SPNs have significantly improved the performance, they still have the following drawbacks. First, the kernel parameters required for updating are not adaptively adjusted to the target map. Second, the kernel scope is fixed during the update process, and multiple iterations are required to obtain long-range dependencies. In this work, we propose the long-short-range recurrent updating network, a novel lightweight deep network framework for depth completion. First, we propose to pre-fill the sparse depth map to the initial depth map by a non-learning method and iteratively updates it to the accurate and dense depth map. The non-learning method used by our work consists of classic image processing operations, such as expansion and corrosion. The initial depth map has coarse but complete scene depth information, which can help relieve the heavy burden of direct regression. Then, we propose a target-dependent update unit to iteratively update the initial depth, which enable our update process to adaptively adjust it to the target map. Specifically, our TDU predicts the sampling position of the neighbors and the weights between them and the reference point by jointly considering the cross-guided and self-guided features. The cross-guided features extracted from RGB images and sparse depths can guide the TDU to avoid irrelevant neighbors, while the self-guided features extracted from the depth map to be updated allow the TDU to be adaptive to the content of the target map. Moreover, our TDU further improves the performance by learning the residual. We observe that when multiple TDUs of the update process employ the cross-guided features of different scales respectively, the TDU guided by smaller scale cross-guided features will adaptively learn to obtain the neighbors in a relatively large scope, and vice versa. Since surrounding points of most pixels in the initial depth are inaccurate. Therefore, at the beginning of the update process, we employ small-scale cross-guided features to lead the TDU to predict a large scope to obtain some long-range but accurate points as neighbors. As the depth map becomes more refined, larger-scale cross-guided features are sequentially used to pay more attention to shorter-range neighbors. According to adjusting the number of channels in different stages of the cross-guided feature extraction network, we obtain 4 LRRU variants across different parameter regimes. We conduct extensive experiments on both indoor and outdoor datasets to verify the performance of our method. Following exiting depth completion methods, we employ the following metrics for quantitative evaluation. Experimental results show that our 4 LRRU variants achieve state-of-the-art performance on NYUV2 and KITTI datasets. Especially, the LRRU base model outperforms SOTA methods on NYUV2 and ranks first on the KITTI benchmark now. There are our qualitative comparison on the NYUV2 and KITTI datasets. Thanks for your attention for our work. Goodbye.